Hey everyone, and welcome to today's Explainer. If you've ever looked up and wondered what's really driving our global climate, well, you are in the exact right place. Today, we're digging into the raw meteorological data to decode the fascinating mechanics of the Earth's weather engine, specifically focusing on unlocking the secrets of the world's jet streams.
So let's start with a massive question. What exactly creates those roaring, 300-knot rivers of air racing high above our heads? To understand these extreme high-altitude jet streams, we actually have to start all the way down at the surface, looking at how massive blocks of air form, move, and eventually collide.
Here's a quick roadmap for today. We'll hit the airmass alphabet, fronts in global circulation, introducing the jet streams, mapping the polar front, subtropical and equatorial jets, and finally, seasonal jet stream shifts. Let's jump in.
Section 1. The air mass alphabet. Before we can even talk about high-speed jet streams, we have to understand the foundational building blocks. Meteorologists actually use a very specific shorthand classification system to track the massive atmospheric systems that eventually create those winds.
The main thing to grasp here is what an air mass actually is. It's basically just a giant, uniform block of temperature and moisture. Imagine an extensive body of air just sitting over an ocean or a continent for so long that its horizontal planes take on the exact temperature and humidity of the surface below it.
And meteorologists track these huge blocks using a really elegant, simple three-letter formula. Track, source region, and temperature. First, does it track over land or water? That's a C for continental, or an M for maritime. Second, the source, polar, Arctic, or tropical. And finally, the temperature relative to the surface, warm or cold. So, for example, maritime polar cold air simply becomes MPC.
Naturally, these categorized air blocks behave totally differently based on their origins. Stable air, for instance, just sort of settles in and creates flat, stratiform clouds. But continental tropical air pulled up from the southern Balkans, that's what triggers those intense European summer heat waves. It's the stark contrast between these specific masses that ultimately provides the raw energy for our global winds.
Section 2. Fronts and global circulation. Now, these giant air masses definitely don't just sit still. As they shift around, global circulation creates distinct wind bands across the planet. We get bands of easterlies forming in the tropical air near the equator, but as you move out into the subtropics, the flow reverses into distinct bands of westerlies.
But here's the real kicker. What happens when warm tropical air slams into freezing polar air? They don't just mix nicely together, they violently clash, and this collision creates what we call the polar front, which is a surprisingly thin, razor-sharp boundary separating those two environments. This specific clash is the spark that ignites the jet streams.
Section 3. Introducing the jet streams.
300 knots. Let that sink in for a second, because that is over 340 miles per hour. When certain upper wind systems align and merge perfectly, they compound their energy to reach these staggering, almost unfathomable speeds.
So, jet streams are essentially fast-moving upper winds, acting as atmospheric rivers circulating the globe. But their behavior isn't static at all. A crucial rule of thumb is that jet streams run much faster and actually physically shift closer to the equator during the winter months. That's because the temperature contrast between the poles and the equator is at its absolute extreme.
Section 4. Mapping the polar front.
Let's zoom in on the incredibly influential Polar Front Jet, or PFJ. If we map the northern PFJ in January, we see it flowing in this massive, sweeping arc from Florida straight across the Atlantic to Folkestone in the UK. It directly follows the mean line of that sharp polar front we talked about. But interestingly, on its own, it usually averages speeds under 200 knots. Now here is a truly wild fact from the data. The track of these jet streams gets heavily bossed around by large landmasses. The massive Siberian high-pressure system literally acts like a brick wall in the atmosphere. It completely blocks the polar front jet over Russia, forcing it to dissipate, only to pick right back up again over Japan. It's like a river hitting a dam and reforming downstream.
Section 5. Subtropical and equatorial jets. Down a bit closer to the equator, we have the subtropical jet, or STJ, which generally cruises at around 90 to 130 knots. But remember that crazy 300-knot figure we mentioned earlier? Occasionally, the subtropical jet merges directly with the polar front jet. They combine to create those super winds before eventually splitting off again with the subtropical jet continuing over the North Pacific.
And there are other highly specialized jets, too. The Arctic and Antarctic jet streams reach about 80 knots, but they only even form during winter, running at about 20,000 feet. On the totally opposite end of the spectrum, you've got an easterly equatorial jet speeding up to 80 knots over the Indian Ocean and Africa, hovering at an absolutely incredible altitude of 50,000 feet.
Section 6. Seasonal jet stream shifts.
Finally, we have to look at how these rivers move over the year. As the Earth orbits, the atmosphere responds dynamically. All the westerly jets physically move north in July, literally tracking the changing angle of the sun. And because July is the dead of winter in the southern hemisphere, that is the exact time those southern hemisphere jet streams hit their absolute peak speeds. If you want to really lock this all in, it helps to distill all these different global jet stream metrics down into a single summary. In meteorology, memorizing these specific altitudes, seasons, and speeds is absolutely critical. Just look at how this data lays out. There is actually a really elegant staircase pattern in the altitudes. The Arctic jet sits at 20,000 feet. The polar front jet steps up to 30,000. The subtropical at 40,000. And the equatorial jet tops out at 50,000 feet. It's a perfect cheat sheet showing how the polar and subtropical jets flow all year round, while the Arctic and equatorial jets are highly seasonal.
So we've seen how simple, uniform blocks of air create sharp boundaries, and how those boundaries ignite into high-speed rivers flowing miles above the Earth. Leaving you with this final thought for the day. As our planet tilts and the sun shifts today, pulling those massive atmospheric currents along with it, where exactly is the jet stream roaring above your head right now? Thanks so much for tuning in to today's Explainer, and we will see you next time.